Next up, we're going to talk about conditional probability. Suppose in an experiment, we've decided we're going to flip a coin 3 times. What then would be the probability that the same face will appear 3 times? Well, using some of the tools that we've seen before, we can consider the sample space as consisting of all the possible combinations of 3 coin flips, where we could have heads, 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 tails, heads, and so on, all through every single possible outcome of 3 flips. So maybe we'll end it with tails, tails, tails. And the size of the sample space, well, using our counting techniques that are now available to us, there are 3 choices we to make. We need to choose 3 things with replacement, and order matters. So that's going to be out of 2 possibilities. So that's 2 to the power 3, which is equal to 8. So what is the probability that the same face will appear 3 times? So the probability of getting the same face is going to be the same as the probability of the event. The only 2 outcomes that correspond to having the same face are heads, 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 and tails, tails, tails. And this is a probability space where every outcome is equally likely. So the size of the space corresponding to the event, or the size of the set corresponding to that event, is 2. There's 2 outcomes in that event, divided by the total size of the sample space, which is 1/4. Okay. Now suppose that I were to tell you that the first 2 flips were heads. What would be the probability of this event now? Well, you would probably argue that there's a 1 in 2 chance that if you know that the first 2 flips are heads, that you're going to get all flips of the same face, because while you have now excluded the outcome tails, 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 in some sense, most of the work has already been done, and really all you need to do is calculate the probability that the last flip is going to be heads. So this is, since this is the last, the probability of the last flip being head, the last flip, one half seems like a reasonable reasonable number. Now that said, we haven't really just built the theoretical tools or the mathematical tools to actually discuss possibilities like this. So this demonstrates the need for what's known as conditional probability, which is a probability of an event given the fact that another event has occurred. So we describe the probability of A given B that has occurred, which is the probability of A given B. That's how we read out that mathematical statement. And the probability of A given B is going to be given below. The probability of A given B is equal to the probability of A and B, or A intersected with B, divided by the probability of B. This formula is perfectly appropriate. In fact, here is kind of a graphical description of what this formula says. Here is our sample space. Here's our event A. Here's our event B. And what this formula says is if we know that B in fact has occurred, then we should ignore all outcomes that don't correspond to B occurring. And then, if we're interested in the probability that A happened given that B occurred, we only need to be concerned with the part of A that also lies in B. So this is the only part that's of interest. But the thing, though, is, so it suggests that whatever we have, it should probably be related to the probability of A and B. The thing, though, is the probability of A and B, if we were to have a probability measure that's just the probability of A and B, that would no longer be a probability measure. Because in that situation, the largest its probability measure could ever get would be the probability of B, which isn't necessarily 1. So we need to renormalize, dividing by the probability of B, so that if we were to ask for the probability of B, that would be 1, and we end up with a valid probability measure. So at some level, we need to renormalize. We are now looking at the A's area in B relative to B. So this part becomes the part that's of interest. So we're looking at now the relative area of A's intersection with B. And if we're saying that we are conditioning on the event B happening, at some level B becomes the new probability space. So we need to divide by the area of B in order to ensure that the resulting probability measure is something such that the probability of this new probability space B would in fact be 1. All right. So, in fact, we can take this formula that we had up here, this formula for the probability of A and B divided by the probability of B. We can come up with a formula for the probability of A and B when we have the probability of A given B by doing some algebra. We have that the probability of A and B is equal to the probability of A given B times the probability of B, just by doing a little bit of algebra, by taking that formula that we had before and multiplying both sides by the probability of B. And in fact, this latter formulation of conditional probability, in my opinion, is almost more useful than just computing the probability of A given B, because it's suggesting that if we want to compute the probability of A and B, which is a quantity that we often frequently need, we can break up this event and think about, well, okay, what's the probability of B happening? And then if we knew that B happened, what would be the probability of A happening? So, and it's almost easier to think of the probability of A and B this way rather than trying to compute it directly. And in fact, the probability of A given B is a proper probability measure. And we get important facts. Like, for example, given the probability of A given B, what is the probability of A complement given B? You feel like what you should have is that it's 1 minus the probability of A given B, and that is, in fact, true. Let's prove this by first considering we have the probability of A complement given B. We're going to have a Venn diagram where we have the events A and B, and so this is going to equal the probability of A complement and B divided by the probability of B, and the region A complement and B is going to be the blue region. Now, what are a couple ways? What's a way we could compute the probability of the blue region? Suppose that we actually had the red region. We could say that the probability of A complement and B, so that corresponds to the blue region, is going to be the probability of B minus the probability of A and B, where A and B is going to be the red region. So we do, in fact, have that probability. If we also additionally had the probability of B, which I will highlight in green. So we therefore have this relationship as well, that this is equal to the probability of B minus the probability of A and B, all divided by the probability of B, which, after you do some more algebra, is equal to 1 minus the probability of A and B minus the divided by the probability of B, which is going to be 1 minus the probability of A given B. Okay, so in fact, we have this formula for the probability of the complement of an event that actually resembles what we had before when we weren't working with conditional probabilities per se. And in fact, it seems that all of the things that we said before about probabilities are true also for conditional probabilities. Everything that we said before is also true for conditional probabilities. All right, so let's do an example. We're going to take that first example that I considered in this section and make it a little bit more rigorous. So using the definition of conditional probability, compute the probability of the event that all 3 coins have the same face when flipped, given that the first 2 flips were heads. So the probability that the first 2 flips were heads, which I will denote like so, is going to be the probability of the event consisting of heads, 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 and heads, heads, tails, which is going to be 1/4. And the probability of the event that the first 2 flips were heads intersected with the event that all the flips are the same, which is the event consisting of heads, 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 and tails, tails, tails. Well, the intersection of those 2 events is going to be just heads, heads, heads. So that's going to be the probability of heads, heads, heads. Okay, heads, which is going to be 1/8. There's only one outcome in this event. So that means that the probability of all the flips being the same, given that the first 2 flips were the same, and well, that the first 2 flips were heads specifically, is going to equal 1/4 over 1/8, which is equal to 1/2. Okay, next example. Suppose that you were dealt 2 cards of a 5-card poker hand, which are going to be the King of Hearts and the 8 of Hearts. Given this information, what is the probability that your complete hand will be a full house? All right, so first off, we should probably compute how many hands contain the King of Hearts and the 8 of Hearts. So I have the King of Hearts and the 8 of Hearts. How many hands have that? Well, let's see. All we need to do, if we know what 2 of the cards in the hand are, is choose the other 3 cards. So choose the other 3 cards. How many hands? How many ways are there to choose the other 3 cards? Well, 2 of the cards in the hand are the King of Hearts and the 8 of Hearts. So there's only 50 cards remaining in the deck, and we're choosing without replacement, and we don't care about the order. So we're going to have 50 choose 3, which after you do some work is going to come out to 19,600. Okay, now we're going to ask ourselves how many hands have how many full house hands? Sorry, my apologies. So how many full house hands have the King of Hearts and the 8 of Hearts? How are we going to form a hand that is a full house hand and contains the King of Hearts and the 8 of Hearts? Well, it's clear that either the 3 card is going to be, either the card that's replicated 3 times is going to be King, or it's going to be 8. And the other card would then be whatever card we selected before. So we could either have 3 kings and 2 8s, or 3 8s and 2 kings. Those are the only 2 possibilities for our full house hand. So we first need to decide which card will be repeated 3 times. So we're going to have to choose the, I'm going to abbreviate this as three-peat. P-A-T. So we're going to have to choose the three-peat card and think about how many ways there are to choose the three-peat card. Then we pick the other 2 cards. We're picking the three-peat card. We're picking the face value of the card. So we need to pick the other 2 suits. And then after we pick the other 2 suits for the three-peat card, we know what the two-peat card will be, or the singly repeated card. We know what it will be, so we don't need to pick its face value, but we do need to pick the other suit. For the twice repeated card. So let's see. First, how many ways are there to choose the card that's going to be repeated 3 times? Well, we could either choose king or we could choose 8. So there's 2 ways to pick that card. Now we need to pick the other 2 suits. Let's say that we chose king, the king of hearts. We need to pick the other 2 suits. So we can't choose hearts because we've already got the king of hearts. So that leaves spades, diamonds, and clubs. So we have 3 possibilities, of which we're going to choose 2. And now we need to pick, if we've chosen king to be the card that's repeated 3 times, 8 will be the card that's repeated twice, and all we need to do is pick the other suit. We cannot pick hearts, so there's 3 suits, and we're going to pick one of those possible suits. So that actually turns out to be 2 times 3 times 3, which is 18. So there's 18 ways to do this. All right, so we are getting close to done. We now need to just compute the probability of a full house, given that you have the king of hearts and the 8 of hearts. And that's going to be the probability of a full house. And that event is intersected with having the king of hearts and the 8 of hearts. And we're going to divide that by the probability of having the king of hearts and the 8 of hearts in our hand. Okay, so here's what we could do. We could say that this is equal to, let's see, we decided that there were 18 full house hands that had the king of hearts and the 8 of hearts, and we're going to divide this by the sample space. That is the probability of the top, because the numerator corresponds to basically the probability of a full house hand with the king of hearts and the 8 of hearts. So we have 18 divided by the size of the sample space for the numerator, and for the denominator we have 19,600 divided by the size of the sample space. The 2 sample space sizes cancel out with each other, so we are left with 18 over 19,600, which is approximately 0.0009. And for what that's worth, that is less than 0.0014, which was the probability of getting a full house. So having the king of hearts and 8 of hearts in your hand makes it more difficult for you to get a full house. And here's some R code that's doing the same thing, basically translating all of that mathematics into R code. All right, next up, suppose your 5-card poker hand is a flush, but this is a quote-unquote flush. This is not a true flush because we are including the possibility of a straight flush, which, as I mentioned before, is generally considered distinct from just your run-of-the-mill flush. What then is the probability that this quote-unquote flush is also a straight flush? So this is going to be the probability of a straight given a flush, which is going to be the probability of a straight flush divided by the probability of a flush. And that's we've already computed these the number of straight flush hands, the number of quote unquote flush hands in section 3. So I'm not going to repeat those computations here. We're just going to have 40 divided by the size of the sample space divided by 5,148 over the size of the sample space. The size of the sample space is canceled out. And in the end, we end up with 40 over 5,148, which is approximately 0.008. Okay, next up, suppose your 5-card hand is a straight. What then would be the probability that it's a straight flush? So we're going to have the probability of a flush given a straight. And that is going to equal the probability of a straight flush divided by the probability of a straight. So all of the calculations from the previous part apply, except the denominator now is going to be different. We're going to have 40 in the top, that's the number of straight flush hands, plus 10,240 hands that correspond to hands that are quote unquote straights, which is going to be, we actually have a nice fraction for this, is 1 over 256, which is equal to 0.004. And for what it's worth, that is less than 0.008, which was the probability of getting a straight flush if you already had a flush, which is suggesting that it's the hard part of getting a straight flush is the flush. So it's easier to get a straight flush with a straight, not with a flush, than a straight. All right, excellent. Excellent. Next example. In a certain village, 20% of individuals are considered wealthy and 35% are considered black. Among blacks, 60% are not considered wealthy. If you choose a random individual from this village, what is the probability that this individual is both black and wealthy? Well, so let's take some of that information and convert it into math. So we've got the probability of being wealthy equal to 0.2. The probability of being black is equal to 0.35. And it's said that among blacks, 60% are not wealthy. So that translates to the probability of not being wealthy, given that you're black, that's going to be 0.6. And correspondingly, the probability that you are wealthy, given that you are black, is going to be 0.4. So that means we want to compute the probability that someone is both wealthy and black. So we want the probability of being black and wealthy, and we want to use this alternate formula that we had that uses conditional probabilities to compute the probabilities of intersection. So this is going to be the probability of being wealthy given that you're black times the probability that you're black. And this is going to be 0.4 times 0.35, which is equal to 0.14. Now, I'm going to ask Now, let's suppose I told you that the probability of being wealthy, given that you're not black, was 0.7. Let's just say that. Would you at all be bothered by the fact that the probability of you being wealthy, given that you were not black, plus the probability of you being wealthy, given that you are black, those don't add up to 1? The answer is no. You shouldn't be bothered by that because, in a sense, it's almost as if they are different probability spaces. And while we require that the two numbers shown here need to add up to 1, we do not require that the probability of A given B plus the probability of A given B complement, we do not require that that equals 1. That is not a requirement. Right. It is in fact possible that it adds up to really just about anything. I'm not really sure if there is a relationship or what it would be, but from my understanding, there's not really much of a useful one. Well, we might see a little bit of a relationship between the two in the form of Bayes' theorem. So before I can talk about Bayes' theorem, which is a very important theorem in probability theory and very frequently used and very frequently cited. In fact, a foundation for almost an alternate school of thought in statistics. We need to first talk about partitions and the law of total probability. A partition is a division of a sample space S into sets A1 through AN, such that for any two sets they are disjoint, and the union of all of those sets is going to be the sample space. Here's an illustration. Here we have the box representing the sample space, and we end up dividing up the sample space into some collection of events. Maybe we'll call it A1, A2, A3, A4, and A5. And every single one of those events are distinct from the others. They are all disjoint events. And yet, the union of all of those events is going to be the sample space because they all form the sample space. Okay, and whenever you have a set A, you always have this basic partition. A very basic partition you have is going to be A and the complement of A, because it literally satisfies that A and A complement are disjoint sets, and the union of A and A complement is going to be the sample space S. So that counts. Once we have this, we have a result known as the law of total probability, which requires that you're working with a partition. It says that if you have some partitioning sets A1 through AN, then if you have any B in this sample space, then the probability of B will be the sum from I equals 1 to n, the probability of B given AI times the probability of AI. Maybe this illustration can help you understand what this theorem is saying. We have the blue region representing some event B, and what you do to compute the probability of B is compute the probability of B given each of these sets. You partition up B across this partition of the sample space S, compute the size of each of these little parts of B, and then add those parts and add those areas together. That's kind of an illustration of what's going on. So then, once we have the law of total probability, another important result is Bayes' theorem, which says if we have a partition of a sample space S, then the probability of any one of the sets in that partition, given the event B happened, is going to be the probability that B happened given that one set happened, or that one event happened, times its probability, divided by the sum from j equals 1 to n, the probability of B given AJ times the probability of AJ. So the denominator in Bayes' theorem is actually computing the probability of B. It is basically a restatement of the conclusion of the law of total probability. Now, that said, this is the general form of Bayes' theorem, but I would say that most of the time what you need is the form in this footnote, where you say the probability of A given B is equal to the probability of B given A times the probability of A, divided by the probability of B given A times the probability of A, plus the probability of B given A complement times the probability of A complement. This part in red is the part that's very frequently placed in textbooks, and it's probably most of the time what you need. Just be aware, though, that in fact it can be generalized to general partitions of a sample space. So Bayes' theorem allows us to compute. It's a probability inversion formula. If you want to know the probability of A given B occurred, you can compute it if you know the probability of B given that A occurred, and the probability of B given that A didn't occur, and also the probability of A. If you have that information, then you're able to invert the probability of B given A, in a sense, and get the probability of A given B. All right, so let's see an example of Bayes' theorem. So we're going to roll a 6-sided die, and then after observing the number of pips, we're going to roll another dice until we get more than that number of pips appearing. What is going to be the probability that the second die roll will show for pips? This is actually not using Bayes' theorem, but rather using the law of total probability. We want to compute so we're rolling a die and we get a number. Let's say that we roll a 4. We're then going to start rolling that dice until we get a number at least as large as 4. So we might roll this dice, we get a 4, and then we're going to roll it again. The first time we roll it, we get a 1. The second time we roll it, we get a 2. The third time we roll it, we get a 6, and then we stop. And we're going to record the number 6. So that's an example of how this works. So what is the probability that the second die roll will show 4 pips? So we're going to work here with, let's see, we'll say that the first die, we'll denote the result of the first die roll with, let's say, Fi. So Fi is the event where first die is I, and Li is the event that the last die is I. Okay, so let's compute the probability that the last die is going to be 4, given that the first die is going to be, let's say 3. Okay. Well, what would that be? If the first die is 3, then the only possibilities for the last die are going to be 3, 4, 5, and 6. And each of those possibilities are going to be equally likely for the last die. So that means that the probability the last die is going to be 4 is going to be one of those, let's see, 3, 4, 5, 6, one of those 4 possibilities, right? And in fact, you could say that the probability that the last die is 4, given that the first die is 4. Well, you got, let's see, 4, 5, 6 as the possible outcomes of the last die. So that's going to be 1 and 3. The probability that the last die is 4, given that the first die is 2, is going to be 1 over 5. And the probability that the last die is 4, given that the first die is 1, well, then just about any dice face is going to be occurring, so that's going to be 1 over 6. Now, the probability that the last die will be 4, given the first die is 5, that will be 0, because the last die is going to be either 5 or 6. So, and similarly, that's going to be equal to the probability that the last die is 4, given that the first die is also 6. That's also the same thing. So now I want to compute the probability that the last die is 4. I want to compute that probability, and I'm going to use the law of total probability for this. This is going to be, according to the law of total probability, the sum from j equals 1 to 6. The probability that the last die is going to be 4, given that the first die is equal to j, times the probability that the first die is equal to j. Well, the probability the first die is equal to j, like that's just going to be 1 and 6, because each of those outcomes is going to be equally likely. So that's going to be 1 over 6, and we're almost done then. So we've got that this is going to be, that this will be 1 over 6 times, so the probability the last die is going to be 4, given the first is 1, so 1 over 6 plus 1 over 5. That's the probability the last die is 4, given the first is 2. Plus the probability the last is 4, given the first is 3. No, that's 4. Sorry. So that's 4. Plus probability the last die is 4, given the first one is 4. And then plus 0 for the other two. So that is all going to add up to... I actually didn't pre-compute this, so I'm going to have to... go to a calculator for this one. Okay, give me a second. All right, so we got 1 divided by 6 times 1 divided by 6 plus 1 divided by 5 plus 1 divided by 4 plus 1 divided by 3. So appears to be that appears to be a repeating 3. In fact, let's verify that by taking this thing out to its entire precision. Yeah, that is probably a repeating 3. So we're going to have 0.1583 repeating as our answer. All right, so that is going to be 0.158 and a repeating 3. Okay, next question. This one is actually using Bayes' theorem. In a city, Uber and Lyft transport passengers. 95% of drivers work for Uber and 5% work for Lyft. One day there is a hit-and-run accident, and a witness claims that she noticed the driver worked for Lyft. Lyft's defense attorneys subject her to testing, and in testing determined that she correctly identifies a car as belonging to Lyft 90% of the time, but will claim a vehicle belongs to Lyft incorrectly 20% of the time. Based on this evidence, how likely is it that the driver who hit the pedestrian worked for Lyft? Do we have some space on this next page? We do. I might want to take some advantage of it. But anyway, so let's start developing some notation and writing and recording the mathematics. Probably going to need to zoom in somewhat to get more space and precision. All right, so let's just say that L represents the event that the driver works for Lyft. So this is work for Lyft. So that means that the complement of L in this scenario will be that they work for Uber. S will be the event that the witness says that it was that the car hit the pedestrian. That the car that hit the pedestrian was with Lyft. So the S corresponds to witness claims Lyft. So the complement of S will be when she says that the car worked for Uber. Okay? So, the probability of the car working for Lyft of the car being a lift car is going to be 0.05. And the probability that the witness says that the car worked for lift, given that the car actually worked for lift, is equal to 0.9. And the probability that the witness says the car was a lift car, given that the car actually worked for Uber, is going to be 0.2. All right, we now have all the information we need to apply Bayes' theorem, because what we actually want to know is what is the probability that the car was a lift car, given that the witness says that the car was a lift car. So we know that the probability of the lift car, regardless of what indifferent to what the witness says, the probability of the car is a lift car is 0.05. But knowing what the lift car is, does it increase or decrease the odds that the car did in fact work for lift? Well, according to Bayes' theorem, this is going to be the probability of S given L times the probability of L divided by the probability of S given L times the probability of L plus the probability of S given L complement times the probability of L complement. And now we can fill in numbers and say this is going to be 0.9 times 0.2 divided by 0.9 times 0.2 plus 0.2 times 0.95. And you can go to a calculator and compute what this is, and you get that this is going to be 18 over 37, which is approximately 0.49. Which, for what it's worth, is less than 0.5, which means that there's two possibilities for the car, and it is true that the odds that the car is a lift car did increase, but it's not above 50%, which means that it's less likely that the car is going to be a lift car, and more likely that the car is going to be an Uber car. So even though the witness claims to have seen a lift car and seems superficially to be accurate, so we might call this a true positive. She seems to have a good true positive rate. Her false positive rate is too high, given the frequency of Lyft and Uber cars in the city. She identifies too many Uber cars as being Lyft cars, and as a result, she is not accurate enough for you to actually confidently believe, or even believe just based on it being the more likely outcome, that the car is in fact a Lyft car. This is one of the examples, by the way. This counts, by the way, as one of those examples I was mentioning where probability theory seems to defy your intuition. But basically what probability theory says is you need to pay attention to the false positive rate of certain procedures. There is actually a book that I saw an example like this. They didn't have Lyft and Uber. That is very much a modern thing. This book predates that. This is a book by a man by the name of Stuart Sutherland. The book is called Irrationality. I think the most recent edition was in 2007. It was a psychology book, and it was one of the first books that got me interested in statistics and probability. I read this book, I believe in my senior year of high school, and I thought it was extremely interesting. And even though I had very, very little, very minimal knowledge of probability and no knowledge at all of statistics beyond the sample mean or the sample median, that was it. And this was one of those profound examples, to me at least in my own life, where probability theory defied what seemed to be basically seemed to defy human intuition, which human intuition seems to pay more attention to the true positive rate than the false positive rate. But the probability theory says you need to pay attention to false positive rate too. Otherwise, just about anything can happen. So, very cool example for me. And like this is more traditionally presented in the case, in the context of like drug testing, where there's a rare disease, and this drug is and they administer a test to determine if a person has this disease, and it has a certain true and false positive rate, and you discover that if the disease is rare enough, it's still unlikely, given a positive result, that the person has the disease. That's kind of the traditional setting for this example, but in honor of Stuart Sutherland and this book early on in my academic career. I wanted to present in terms of cars. He used the green cab company and the blue cab company, but I used Uber and Lyft because it's 2020. All right, so that's it, and I will see you in section 5 on independence.